Welcome to Science Pills. We spend our entire lives interacting with a reality that feels so incredibly solid,
Yeah, thankfully.
right? Like you sit in a chair and it holds you up, you walk through a doorway, and you don't suddenly, I don't know, ripple into a wave of probability and splash against the doorframe.
That would make the morning commute pretty difficult.
Exactly. I mean, you take the solidity of the world entirely for granted.
We all do. It's the ultimate illusion, really. The macroscopic world we inhabit is just so comfortingly predictable.
Yeah, it has sharp edges.
Definite locations. You drop a set of keys, they fall to the floor. They don't simultaneously exist on the ceiling and the kitchen counter.
But, and this is where today's deep dive gets wild, the deeper you look into the physics of how those keys are actually constructed, the more that solid reality starts to look like a very precarious magic trick.
Oh, absolutely. The foundations are incredibly shaky when you really zoom in.
Right. So today's sources range from undergraduate physics papers about the quantum wavelength of a cow.
Which is a fantastic paper, by the way.
It's amazing. And we're going all the way to ancient Chinese meteorites and then to the catastrophic energy grid demands of modern artificial intelligence.
It sounds like a completely random stack of topics.
It really does. But they all point to one deeply unsettling question for you, the listener. What is actually holding our reality together? We are going to explore the bizarre, invisible boundary between the microscopic quantum world, where things are inherently blurry, and our everyday classical reality.
Yeah, the transition between those two worlds.
Exactly. And the theory we are building toward today suggests that the vast, relentless expansion of the cosmos itself might be the very thing anchoring you to your chair right now.
It is arguably one of the most profound foundational mysteries in modern physics. I mean, we have two wildly successful rule books for the universe that absolutely refuse to talk to each other.
Right, the big and the small.
Exactly. We know quantum mechanics works flawlessly for the tiny stuff, atoms, electrons, photons, and we know classical mechanics works perfectly for the big stuff, like baseballs, planets, you and me.
But the middle ground is a mess.
A total mess. Finding the exact mechanism that transitions a system from that quantum fuzziness to classical sharpness, that is a theoretical tightrope. We are basically looking for the exact mechanism that forces matter to choose a location and just stay there.
So, I mean, to understand how reality stays sharp, we have to start by looking at how the blurriness was discovered in the first place.
Yeah, we have to rewind a bit.
Let's go back to the year 1900. There's a physicist named Max Planck,
Right?
and he is wrestling with something called the black body radiation problem.
So, to set the scene for you here, at the end of the 19th century, classical physics was in a state of quiet crisis. Physicists were trying to understand how heat and light interacted. Specifically, every physical body spontaneously emits electromagnetic radiation based on its temperature. Like if you heat up a piece of iron in a forge, it first glows a dull red, then bright orange, then a blinding bluish white as it gets hotter.
Right, which makes intuitive sense. Hotter object, higher energy light.
Exactly. And physicists had equations to describe this. They had something called Wien's law.
Wien's law, yeah.
And it beautifully predicted that color shift. It explained why the peak emission moves to shorter, bluer wavelengths as temperature rises. Think of Wien's law as the rule that explains the visual color change of hot metal.
But it wasn't perfect.
No, it failed at long wavelengths. So another team came up with the Rayleigh-Jeans law.
Okay, another equation.
Right, and that one worked perfectly for those longer, lower frequency waves like infrared and radio.
But here's the problem our sources highlight. When classical physicists tried to combine these rules to create, like, one unified theory of how an object emits heat and light, the math completely broke reality.
It was a disaster.
Classical electromagnetism essentially predicted that an ideal emitter, like an oven at thermal equilibrium, would pump out an infinite amount of high-frequency ultraviolet radiation.
Which is clearly not what happens.
Right. They called it the ultraviolet catastrophe, which, I gotta say, is a great name for a band, but a terrible day for physics.
It's a very bad day.
Because if the classical math was right, every time you try to bake a potato in your oven, you would unleash a lethal, infinite burst of ultraviolet and gamma radiation.
Your kitchen would just vaporize.
Yeah. And since kitchens were notably not vaporizing, the theorists knew their foundational understanding of energy was fundamentally broken.
So Planck, who was actually deeply conservative in his approach to physics, spent months trying to make the math fit the actual experimental data of what ovens and heated objects really do.
He was trying to save classical physics.
He was, but finally he did something he later described as an act of desperation.
He broke the universe into chunks.
He did. Up until that point, classical physics assumed that energy flowed continuously.
Like a stream.
Exactly. Think of it like pouring water from a pitcher into a glass. The flow of water is smooth, uninterrupted, and you can pour any infinitely small fraction of a drop if you want to.
Right.
But Planck hypothesized that the energy of the atomic oscillators emitting this light wasn't a continuous flow at all. Instead, it was quantized.
Meaning, to use the water analogy, he discovered that what we thought was a continuous stream of water is actually made up of millions of microscopic, indivisible, rigid glass marbles.
That's a great way to put it.
You can pour one marble, or two marbles, but you can never pour half a marble. Energy comes in discrete packets.
And to make the math work for these energy packets, Planck had to introduce a brand new constant of nature. We now call it the Planck constant, denoted by the lowercase letter h.
And it dictates the size of the marbles.
Exactly. This constant determines the fundamental size of those marbles of energy.
And the value of h is insanely small.
Astronomically small. Its value is roughly 6.626 times 10 to the power of negative 34 joule seconds.
So that's a decimal point, 33 zeros, and then 6626.
Right. Because this foundational number is so minuscule, the chunks of energy are unimaginably tiny.
Which is why we don't notice them.
Exactly. That is why everyday reality feels smooth and continuous to us when we interact with it. We are simply too massive and our senses are too blunt to notice the individual marbles of energy.
It's completely outside the realm of human perception. So Planck introduces this mathematical desperation in 1900.
Yeah.
Fast forward to 1905, and Albert Einstein comes along, looks at Planck's work, and realizes it's not just a mathematical trick for ovens.
No, it was physical reality.
Einstein uses Planck's constant to explain the photoelectric effect, proving that light itself, the actual electromagnetic field, is physically made of these quantized packets, which we now call photons.
That was a monumental paradigm shift.
I bet.
I mean, for centuries, experiments had conclusively shown that light behaved as a continuous wave. It diffracted, it interfered with itself. But Einstein proved it also behaved as a discrete particle. Light had a dual nature.
But the rabbit hole goes so much deeper than light. In 1923, a French physicist named Louis de Broglie flipped Einstein's script entirely.
Oh, this is where it gets fun.
De Broglie asked a very simple, very dangerous question. If light, which we've always thought of as a wave, can sometimes act like a physical particle, what if solid matter, which we've always thought of as particles, can act like a wave?
It was an incredibly audacious leap of logic.
Just totally backwards.
Yeah. De Broglie proposed that wave-particle duality applies to everything in the universe. Absolutely all matter has an intrinsic wavelength. And he provided a shockingly simple equation to prove it.
Okay, let's hear the math.
It's just lambda, which is the symbol for wavelength, equals Planck's constant h, divided by p, which is the momentum of the object.
Just to make sure we're totally grounded here, momentum is just an object's mass multiplied by its velocity, right? Like how heavy is it and how fast is it going?
Correct. So the de Broglie wavelength implies something staggering about the nature of reality. Everything is waving.
Everything.
Everything. The Earth orbiting the sun is a wave. A baseball thrown by a pitcher is a wave. An electron is a wave. And you, sitting in your chair listening to this, are a wave.
Okay, let's actually run the numbers on this because this where one of our sources gets wonderfully absurd. Let's calculate the wavelength of a human being.
I love this thought experiment.
We have a physics breakdown here that does the math. Let's say we have an average adult human with a mass of 70 kilograms. And let's say they're taking a leisurely stroll down the street at a velocity of 1 meter per second.
So their momentum is simply 70 kilogram meters per second.
Right. We take that incredibly tiny Planck constant, the 6.626 times 10 to the negative 34, and we divide it by 70.
Which gives us...
The result is a wavelength of about 9.5 times 10 to the negative 36 meters.
So small.
And if that same human decides they are running late and picks up the pace to a brisker 1.4 meters per second, their momentum increases. Because momentum is the denominator in the equation, as momentum goes up, the wavelength gets even smaller.
It shrinks.
Yeah, it shrinks to about 6.78 times 10 to the negative 35 meters.
We really need to pause and unpack just how small that number is, because human brains aren't built to comprehend 10 to the negative 35.
No, we really aren't.
Let's look at a single proton, which sits in the nucleus of an atom. A proton is already unfathomably small. It's roughly 10 to the negative 15 meters across. That human walking down the street has a wavelength that is roughly 20 orders of magnitude smaller than a single proton.
That is, that's a factor of 100 quintillion. It's almost meaningless to try and visualize.
It is entirely beyond physical intuition.
But our sources take this thought experiment even further. There's an actual paper published in an undergraduate physics journal from the University of Leicester, and the title is just perfect.
Oh, I know this one.
It's called The Wavelength of a Cow.
It's a fantastic exercise. It perfectly illustrates what happens when you take the rules of quantum mechanics and brutally force them onto the macroscopic classical world.
It's so funny. The students who wrote it took an average cow, assuming a mass of about 630 kilograms. Then they researched the absolute top speed of a frightened cow.
As one does.
As one does in physics,
Yeah.
which apparently is about 7.8 meters per second.
Yeah.
So when you plug that massive momentum into de Broglie's equation,
Dividing the tiny Planck constant by a heavy, fast-moving cow.
exactly, the cow's wavelength comes out to 1.3 times 10 to the negative 37 meters.
And this is where the physics moves from just being fun math into a profound statement about the limits of our universe. We need to compare the cow's wavelength to something called the Planck length.
Right, which is different from the Planck constant we've been using in the equation.
Yes, entirely different. The Planck length is derived from a combination of fundamental constants, and it comes out to roughly 1.6 times 10 to the negative 35 meters.
Okay.
In theoretical physics, the Planck length is essentially the fundamental limit of distance. It is the pixel size of the universe.
Pixel size.
Yeah, it is the smallest scale at which the fabric of space and time actually has any understandable geometric meaning. If you try to measure a distance smaller than the Planck length, our current models of gravity and quantum mechanics completely break down into mathematical nonsense.
Like physics just gives up.
Essentially, yes. Concepts like left, right, before, and after cease to exist.
So wait, the running cow's wavelength is 1.3 times 10 to the negative 37. The Planck length is 10 to the negative 35. That means the cow's wave nature is almost 2 full orders of magnitude smaller than the absolute smallest measurable distance in physics.
Precisely.
That's crazy.
So when people ask, why don't I see the wave nature of everyday objects, the answer isn't just that our microscopes aren't powerful enough. The answer is that the cow's wave is physically, fundamentally impossible to observe in our universe. It is smaller than space itself.
Wow.
Because Planck's constant is so infinitesimal, these wave effects only dominate when you are dealing with incredibly tiny masses, like a single electron. Or when you cool atoms down to temperatures a fraction of a degree above absolute zero, where their momentum drops so low that their wavelength finally stretches out to a measurable size.
But for a hot, heavy, fast-moving cow.
The wave is entirely erased from reality.
Okay, I have to push back here. And this actually came up in one of our sources from a physics stack exchange forum. A user asked about this exact thing, calculating their own de Broglie wavelength. And the physicists in the comments got into a fairly heated debate about whether calculating the wavelength of a cow or a human is even mathematically or physically sound in the first place.
Oh, it's a very valid critique. The de Broglie equation is elegant and simple, but the physical reality of a macroscopic object is a nightmare of complexity.
Exactly. The critics on the forum pointed out that a human, or a cow, isn't a single rigid point particle flying through a vacuum.
No, we're not marbles.
We are incredibly messy. We are a thermodynamic soup. A human body is composed of roughly 7 octillion atoms, and because we exist at room temperature, about 300 Kelvin, every single one of those atoms is vibrating, bouncing, and colliding wildly.
It's utter chaos inside there.
Yeah. Your heart is beating, blood is rushing through your veins, your lungs are expanding and contracting. All of those internal parts have their own distinct velocities and momentums.
Yeah.
So isn't it just mathematical fiction to assign a single clean wavelength to the center of mass of a complex, hot system?
Well, from a purely pragmatic standpoint, yes, the critics are right. It's a mathematical novelty.
Okay.
As one physicist in that source noted, quantum mechanics is fundamentally swamped by thermodynamics at the macroscopic scale. The random, chaotic thermal jiggling of all those octillions of atoms, what we call thermodynamic noise, completely washes out any delicate, coherent wave pattern you might try to assign to the entire object.
It's just scrambling the signal.
Exactly. The
Yeah.
waves of all your individual atoms are interfering with each other destructively. To even theoretically observe a macroscopic object acting as a single quantum wave, you would have to cool it down to incredibly near absolute zero to quiet all that internal thermal motion.
But there was another point raised in that forum that I found deeply unsettling. Let's look at the de Broglie equation again. Wavelength equals Planck's constant divided by momentum. And momentum is mass times velocity.
Right.
So what happens if I'm not walking down the street? What if I just sit in my chair and I make my velocity 0?
Well, if your velocity is 0, your momentum is 0.
Right. And if you divide Planck's constant by 0, the math blows up.
It does.
The wavelength becomes infinite. If I manage to sit perfectly, mathematically still, does my probability wave suddenly stretch across the entire universe? Does my physical location become completely undefined?
That is the zero velocity paradox.
The zero velocity paradox.
Yeah, and it is not just a quirk of division. That paradox, the idea of an object with zero velocity having an infinite wavelength, leads us directly into the deep, dangerous waters of quantum mechanics. It brings us face to face with the problem of localization and the terrifying threat of Heisenberg's uncertainty principle.
Let's dive into that, because if the universe actually worked the way that divide by zero math suggests, everyday life would be a hallucination.
It would be unlivable.
Right. You'd sit down at a red light, your velocity would hit 0, and your car would instantly smear across the galaxy. Obviously, that doesn't happen.
To understand why it doesn't happen and why localization is such a massive puzzle, we have to talk about Werner Heisenberg.
Okay.
In 1927, he introduced a principle that entirely shattered the classical idea of a clockwork universe. In classical physics, the assumption was always that if you had a good enough measuring device, you could know the exact position and the exact momentum of any object simultaneously.
Meaning you could know exactly where a particle is and exactly where it is going at the exact same time.
Right. But Heisenberg proved that this is fundamentally impossible. The uncertainty principle states that there is a hard limit to the precision with which certain pairs of physical properties can be known simultaneously.
And the most famous pair is position and momentum.
Exactly. The math dictates that the uncertainty in an object's position, multiplied by the uncertainty in its momentum, must always be greater than or equal to Planck's constant divided by 4 pi.
I think a lot of people misunderstand this. They think it's an engineering problem. Like, oh, our microscopes are just a bit clumsy and the light we shine on the atom knocks it out of place.
That is a very common misconception. It's often taught that way as a crutch, but it's wrong.
Oh, really?
Yeah. The uncertainty principle has nothing to do with the clumsiness of our instruments. It is an intrinsic, unavoidable property of the wave nature of reality itself. It's about how waves mathematically function.
Can we unpack that mechanism? Why does knowing a wave's location destroy its momentum?
Think about what a wave is. A pure wave with a very clear, measurable, and single wavelength is a repeating pattern of peaks and troughs. Because the wavelength is perfectly uniform, we know its momentum exactly, thanks to de Broglie.
Okay, that makes sense.
But ask yourself, where is that wave located?
Well, it's everywhere. It's spread out infinitely in both directions.
Exactly. A pure wave has no single position. Now, what if you want to create a localized particle? You want a wave that only exists in one tiny spot, like a spike. To build that localized spike mathematically, you have to add together infinite numbers of different waves, all with different wavelengths, overlapping them so they cancel each other out everywhere except for that one tiny localized spot.
Oh, I see. So because you've squished it into a single spot to give it a definite position, you no longer have one clear wavelength.
Right.
You have a massive, chaotic jumble of overlapping wavelengths.
And because you have many wavelengths, you have many possible momentums. The momentum has become wildly uncertain. You simply cannot construct a wave that has both a single definite position and a single definite wavelength. The universe forbids it.
My favorite way to visualize this, and I think it perfectly captures the violence of the math, is to imagine squeezing a water balloon.
That's a great analogy.
Imagine the balloon as a particle. Squeezing the balloon in your hands is the act of localizing it, giving it a strict, defined position. You're forcing the uncertainty in its position to become very small. What happens to the water inside?
The water violently bulges out in unpredictable directions between your fingers.
Exactly. That bulging, escaping water is the momentum becoming uncertain. You squeeze the position tight, and the velocity bulges out of control. You can never contain both at the same time.
That is a superb analogy because it explains the physical trade-off. And it perfectly explains the paradox of the unconstrained free object we discussed earlier.
The divide by zero thing.
Right. If an object is completely at rest, meaning its velocity and momentum are exactly 0, then the uncertainty in its momentum is also 0. We know its momentum perfectly.
And according to Heisenberg's water balloon, if the momentum uncertainty shrinks down to 0, The position uncertainty has to bulge out to infinity to maintain the balance of the equation.
Precisely. In quantum mechanics, an object perfectly at rest is described mathematically by a probability wave that extends uniformly throughout all of space. It has completely lost its physical location.
That is wild.
It is equally likely to be found literally anywhere in the universe. It is entirely fuzzy.
So we're back to the core mystery. If I sit perfectly still in my chair, why don't I dissolve into an infinite probability wave?
Because you aren't fuzzy.
Right, why do I stay localized? My velocity feels like zero. My momentum feels like zero. I am not fuzzy.
This is the crux of the quantum classical transition. Because if Heisenberg is right, to localize an object, to force your body in your chair to have a definite position, you must introduce uncertainty in its motion.
You had to squeeze the balloon.
Any localized wave packet naturally wants to spread out and smear over time. If you squeeze the water balloon, the water has to move.
So for humans and coffee cups and chairs to exist in a sharp, localized, non-fuzzy state, something must be constantly squeezing our position.
Exactly.
And if our position is being squeezed, something must be constantly injecting uncertainty into our velocity. But I don't feel it. My coffee cup on the desk seems perfectly solidly still.
It seems still to us from our limited macroscopic perspective, but what if there was a mechanism, an invisible, ubiquitous force that was already providing an intrinsic uncertainty and velocity to everything around us?
Like a background noise?
Exactly, something that operates constantly on such a grand scale that we don't even notice it on a local level, but mathematically it's doing the heavy lifting to keep us solid.
And this brings us to the main event of our sources. This is C.L. Herzenberg's theory. The idea that the vast, expanding cosmos itself is what anchors the classical world.
It's a breathtakingly elegant theory.
It really is.
C.L. Herzenberg published a paper attempting to answer this exact mystery. Why do large objects behave classically, with sharp edges and firm locations, while extremely small objects succumb to quantum fuzziness? And the solution proposed bridges the smallest scales of quantum mechanics with the largest scales of cosmology.
Specifically, Herzenberg points to the expansion of the universe, Hubble's law.
Yes. Edwin Hubble's observations in the 1920s proved that the universe is expanding. We see distant galaxies receding from us in all directions.
Right.
But a crucial distinction needs to be made here. It is not that galaxies are acting like shrapnel, flying outward through static, empty space after a giant explosion.
Which is how everyone pictures the Big Bang.
Right. But it's wrong. It is the fabric of space itself that is stretching. The grid lines of the universe are getting further apart. Every point in space is moving away from every other point.
I struggle to picture this sometimes, because when we talk about cosmic expansion, we are almost always talking about massive astronomical scales, billions of light years, distant quasars.
Right, the macro.
Yeah, we think of it as something happening out there in the deep void.
Hmm.
We don't think about the space expanding between my nose and this microphone.
That is our intuition, yes.
Yeah.
But if the expansion is a fundamental geometric property of space-time itself, then it isn't just happening out in the void, it must be happening everywhere, across all scales.
Even small scales.
Even at microscopic scales,
Yeah.
even inside solid objects. The space inside your coffee cup, the space between the carbon atoms making up your desk, that spatial environment is theoretically being subjected to the exact same stretching.
Wait, if the space inside my coffee cup is expanding,
Yeah.
why isn't the cup slowly getting bigger? Why isn't the handle moving away from the rim?
Because the forces holding the cup together, the electromagnetic bonds between the molecules, the strong nuclear forces inside the atoms, are vastly, unimaginably stronger than the incredibly gentle, incredibly weak pull of cosmic expansion at that small scale.
Oh, I see.
The physical matter of the cup easily resists the stretching. It doesn't get ripped apart.
Okay, so the cup holds its shape.
It holds its shape, yes. But the actual spatial coordinate system within the volume of the cup is still expanding, and Hubble's law has a very specific, mathematically rigid feature.
Which is?
The recession velocity, the speed at which 2 points in space move apart from each other, increases linearly with the distance between them.
So the farther apart two things are, the more expanding space there is between them, so the faster they recede from one another.
Correct. Now, think about what this geometric reality means for an extended physical object like a coffee cup. A larger object encompasses more physical volume, meaning it encompasses more expanding space.
Okay, tracking.
Therefore, The difference in Hubble expansion velocities between an atom on the far left side of the cup and an atom on the far right side of the cup is greater than it would be for a tiny object.
Let me make sure I'm fully wrapping my head around this.
Yeah.
Because my coffee cup is, say, 10 centimeters across. The space on the left side of the cup is technically receding from the space on the right side of the cup due to the universe expanding.
Yes.
And this creates a built-in intrinsic velocity spread inside the physical volume of the object.
Exactly. The object encompasses a range of velocities simply by existing across a volume of expanding space. Now, let's look at the actual numbers Herzenberg calculated, because they initially seem completely insignificant.
Okay.
If you have an object about 1 centimeter in size, the Hubble expansion velocities from one side of that object to the other are microscopic. We are talking on the order of 10 to the negative 18 centimeters per second.
10 to the negative 18. That is a billionth of a centimeter per second. It's absolute fraction of a snail's pace. It is completely undetectable by any instrument we possess.
Yeah.
It feels like it shouldn't affect anything at all.
It is entirely undetectable, but we have to bring this back to Heisenberg. Remember the uncertainty principle.
Position uncertainty multiplied by momentum uncertainty must be greater than Planck's constant.
And remember how astronomically small Planck's constant is. 10 to the negative 34.
Right.
So you have an incredibly tiny constant governing the rule, and now you have an incredibly tiny built-in velocity spread caused by the expanding universe.
Oh, I see where this is going.
When you take this tiny velocity spread caused by the cosmos and you plug it into the uncertainty principle as your baseline velocity uncertainty, the math works absolute magic.
Let's walk through that math. The equation Herzenberg uses is a fascinating approximation. It states that the uncertainty in an object's position, the quantum fuzziness, delta x, is roughly equal to Planck's constant h divided by 4 pi times the mass of the object times the Hubble constant times the linear physical size of the object.
Yes. So Herzenberg took the numbers for a standard 1 centimeter object of ordinary mass. He plugged in the mass, the 1 centimeter size, and the Hubble constant of the universe.
And what popped out?
The math revealed that this tiny, undetectable intrinsic velocity spread from the cosmos reduces the positional uncertainty of that object down to roughly 10 to the negative 9 centimeters.
10 to the negative 9 centimeters. That is smaller than the diameter of a single atom.
It is phenomenally small. It means the 1 centimeter object is firmly, resolutely localized. It has a well-defined position. It behaves perfectly classically.
Wow.
The cosmic expansion has squeezed the water balloon of its position just tight enough to lock it into solid reality without injecting so much velocity uncertainty that it blows the object apart.
That is deeply profound. The cosmos itself is doing the squeezing.
It is.
But what happens is objects get smaller, like a grain of sand, a bacterium, an atom. As the object shrinks, the volume of expanding space inside it shrinks too. So the spread of Hubble velocities must get smaller.
Precisely. As you scale down the physical size of the object, the intrinsic velocity uncertainty provided by cosmic expansion drops dramatically.
And the uncertainty principle is a seesaw.
Exactly. If the velocity uncertainty goes down, the position uncertainty, the quantum fuzziness, must go up. Herzenberg calculated the threshold where this transition happens.
Where's the line?
When you scale down to an object size around 0.1 millimeters, which is roughly the mass of a microgram, like a tiny speck of dust,
Okay.
the positional uncertainty calculated from the Hubble expansion balloons outward until it becomes comparable to the actual physical size of the object itself.
So a microgram speck of dust is theoretically fuzzy to the scale of its own body. Its edges begin to blur mathematically.
Yes, this is the boundary line. This is the threshold where quantum fuzziness begins to dominate the classical world.
That's amazing.
If you go even smaller than a microgram, down to a single molecule or an electron, the physical volume is so tiny that the Hubble expansion inside it is pathetic. It provides almost zero velocity uncertainty.
So the balloon pops out the other side.
Exactly. Heisenberg's law demands that the position uncertainty explodes outward, becoming much larger than the object. The electron entirely loses localization. It ceases to be a classical object and becomes a smeared-out quantum wave.
This completely changes my understanding of reality.
Yeah.
You're telling me that the grandest, most mind-boggling scale of the universe, the literal expansion of space-time across billions of light years, is micromanaging the physical state of my coffee cup to make sure it doesn't quantum tunnel through my desk.
It is a breathtaking synthesis of cosmology and quantum mechanics. Herzenberg points out that one of the great mysteries of the quantum classical transition has always been its incredible robustness.
What do you mean?
Well, it doesn't matter what materials you use. You can bond together carbon or iron or plastic. You can heat it up or cool it down. Regardless of the material, if you assemble enough mass and size, you reliably and unavoidably get classical behavior.
Why?
If Herzenberg's theory is correct, it's because the transition doesn't care about chemistry. It only depends on physical size and mass interacting with the geometric expansion of spacetime.
The only reason we live in a sharp, classical world is because we live in an expanding universe.
That is the implication, yes.
Okay, my mind is thoroughly blown. But we need to see how this plays out in the real world. If the vacuum of expanding space is what actually localizes matter and dictates the rules of physical reality, what kind of chemistry is actually happening out in that deep space vacuum before it ever reaches a planet?
It's a great question.
We have 3 recent scientific discoveries in our sources that ground this grand cosmic theory, proving that the universe isn't just a passive backdrop. It is actively participating in our chemical, historical, and technological evolution.
Let's hear them.
Let's start with the first discovery, the asteroid Ryugu.
Oh, this is a perfect bridge from theoretical physics to tangible chemistry. In 2020, the Japanese spacecraft Hayabusa 2 accomplished an incredible feat. It intercepted a near-Earth asteroid named Ryugu, collected pristine samples of the rock and dust, and successfully returned them to Earth.
And scientists have been rigorously analyzing these samples in sealed, clean environments to ensure no earthly contamination. And the announcement they just made is monumental. They have now definitively detected all 5 fundamental nucleobases in those extraterrestrial samples.
Adenine, guanine, cytosine, thymine, and uracil. These are the molecular letters that make up the genetic code of DNA and RNA. They are the absolute foundational blueprint of all known life.
So wait, if the building blocks of life are just sitting there on a barren asteroid like Ryugu, that implies biology isn't just some rare, miraculous Earth trait. It's a fundamental physical property of the universe, just like gravity or thermodynamics.
That is exactly the insight we should take from this. We just spent 20 minutes discussing how macroscopic classical reality emerges from quantum building blocks under the influence of cosmic expansion.
Right.
Well, here we see the complex, localized chemical building blocks of life being forged in the deep, cold, radiation-soaked vacuum of space. The universe is acting as an active chemical laboratory.
It's prefabricating life.
Exactly. It is prefabricating the components of biology in the dark long before they ever crash into a warm, wet planet. It reinforces this central theme that our existence, right down to the DNA in our cells, is intimately and directly tied to deep cosmic processes.
Which flows seamlessly into the second discovery, bridging the gap from our chemical origins to human history. We look at an archaeological site in southwestern China called Sengxingji.
A fascinating site.
This is a sacrificial site from the Bronze Age, already famous for unearthing these massive, almost alien-looking bronze masks. But archaeologists recently discovered something that shifts our entire understanding of their technology. They unearthed the earliest Bronze Age meteoritic iron artifact ever found in China.
It is a remarkable find. Finding meteoritic iron at a highly advanced ritual site like Sengxingri tells us a profound story about humanity's relationship with the sky.
Try to put yourself in the shoes of an ancient Bronze Age metalsmith. Your entire technological world revolves around smelting copper and tin. You don't have the furnaces or the knowledge to extract iron from terrestrial ore. The melting point is just too high.
You're limited by your thermodynamics.
Exactly. But one night, you look up and see a streak of fire fall from the heavens. You track the impact. You find this heavy, dark, incredibly tough magnetic rock sitting in a crater. And through sheer trial and error, you figure out how to forge it.
The visceral imagery of that is awe-inspiring. These ancient people were encountering a material forged in the hearts of dying stars, delivered by the mechanics of the solar system, and they recognized its power.
Humans were literally taking pieces of the cosmos that fell to Earth to build their earliest advanced tools. We didn't just passively live in the universe, we weaponized it.
We did!
We harnessed the stars to build tools before we even knew how to dig iron out of our own planet.
It shows a continuous thread of cosmic interaction. The cosmos dictates the quantum rules that allow iron to be solid in the first place. The solar system delivers that iron via asteroids. And human consciousness, driven by curiosity and necessity, harnesses it.
Right.
But there is a fundamental limit to how much we can simply extract and harness, which brings us to the final and perhaps most pressing discovery in our sources regarding our immediate future.
Yes. We learned to harness space rocks, And now we are harnessing silicon to build artificial intelligence. But we are hitting a catastrophic wall.
The energy limit.
The third discovery revolves around the energy crisis of computing and the development of something called neurosymbolic AI. Our sources highlight a terrifying statistic from the International Energy Agency. They estimate that in the year 2024, artificial intelligence and data centers in the United States consumed an absolutely staggering 415 terawatt-hours of power.
To put that 415 terawatt hours into perspective, that is more than 10% of the total electricity demand of the entire United States.
That is insane.
It is an entirely unsustainable trajectory. We are trying to build artificial brains, systems that can reason, create, and solve complex problems, but we are using brute force classical computing architecture to do it. We are building massive server farms, processing unimaginably huge data sets, and we are slamming headfirst into the hard thermodynamic limits of energy generation.
It feels incredibly primitive when you put it in the context of this whole discussion. We are burning through 415 terawatt-hours of classical thermodynamic energy, literally boiling water with coal and gas to spin turbines, to power an AI that we hope will eventually be smart enough to unravel the deepest quantum mysteries of the universe.
It is deeply ironic.
Are we just stubbornly brute-forcing a problem that the universe itself solves effortlessly?
That is the central irony of the modern age. Think about what we've learned today. The universe does not waste energy. It uses fundamental physical laws, like the infinitesimally small Planck constant and the ambient geometric expansion of space-time to govern the reality of septillions of atoms with perfect, elegant efficiency.
The universe is the ultimate optimized computer.
Exactly. The universe calculates the wave function collapse and the localization of a microgram of matter instantaneously everywhere all at once without breaking a sweat. It doesn't need a cooling tower. Meanwhile, we require a nuclear power plant to train a language model to write a decent poem.
So how do we fix it? The source highlights neurosymbolic AI as the path forward. But what exactly is that, and how does it mimic the efficiency of physics to save our power grid?
Neurosymbolic AI is a fundamental rethinking of how we structure artificial intelligence. It's an attempt to merge two entirely different, historically opposed approaches to computing.
Okay, what are the two sides?
On one hand, you have neural networks. These are the systems behind things like image generators or large language models. They are incredibly good at pattern recognition, intuitive leaps, and learning from massive data sets. But they are statistical black boxes, and they require gargantuan amounts of energy to train.
Right, they just brute force their way through millions of examples until they find the pattern.
Exactly. On the other hand, you have symbolic AI, which is older. Symbolic AI uses human-readable logic, explicit rules and symbols to solve problems.
Like, if X, then Y.
Right. It's much more transparent, highly energy efficient, and capable of strict logical deduction, but it is rigid and terrible at dealing with messy, real-world data.
So neurosymbolic AI is mashing them together. It's like giving the AI a fast, intuitive, pattern-recognizing brain paired with a slow, logical, rule-following brain.
Precisely.
So it doesn't have to spin up a massive, power-hungry neural network just to solve a basic logic puzzle that a simple rule could answer instantly.
Exactly. By combining them, developers aim to slash energy use dramatically while actually improving performance. The AI becomes capable of true logical reasoning, not just statistical guessing based on a data set.
That makes so much sense.
And if we zoom out to the cosmic perspective, this is a necessary evolution. If we want to build better brains, we have to start respecting the physical limits of energy. We have to design systems that mirror the elegance of physics, using distinct, efficient rules tailored to the scale of the problem, rather than just throwing more electricity at a server rack.
It all comes back to efficiency and limits. Let's take a breath and weave this incredible journey together, because we have covered a massive amount of conceptual ground today.
We really have.
We started by looking at the sheer mathematical absurdity of trying to calculate a cow's de Broglie wavelength. We realized that macroscopic wave properties are fundamentally impossible to observe because they're smaller than the Planck length, smaller than the pixel size of space itself.
We then plunged into the terrifying implications of Heisenberg's uncertainty principle, discovering the physical mechanism of localization. To have a definite position, an object's momentum must be inherently uncertain. If you squeeze the water balloon, the water bulges.
And that led us to the big aha moment. C.L. Heisenberg's profound theory that the relentless, invisible expansion of the cosmos, the very stretching of space-time happening inside the atoms of your coffee cup, provides just enough built-in velocity uncertainty to anchor reality.
Universe micromanages our classical world.
A cosmos that we then saw actively participating in reality. We saw the universe acting as a quantum chemistry lab, forging the nucleobases of life on the asteroid Ryugu. We saw ancient humans at Sangsing forging tools from the iron cores of fallen stars. And finally, we saw how our modern pursuit of artificial intelligence is forcing us to reckon with the very thermodynamic limits that the universe so elegantly navigates.
It's an overwhelming perspective shift.
It really is. Every time I look at a solid object now, like a chair, a cup, my own hands, I'm going to picture it secretly stretching just a tiny bit on the inside, constantly interacting with the edge of the cosmos, just to avoid turning into a quantum blur. It makes reality feel like an ongoing active process rather than a static given.
It's a very active universe.
But before we wrap up, I know you have a final, slightly terrifying hypothetical for us based on everything we've discussed today.
I do. I want to leave you with a thought experiment derived directly from Herzenberg's theory. We have spent this deep dive establishing that the continuous expansion of the universe provides the intrinsic velocity spread that forces macroscopic objects to have definite, sharp locations.
Right. Keeps the water balloon squeezed.
It keeps the balloon squeezed. But cosmologists do not know for certain how the universe will ultimately end.
Right. There are theories that the expansion might accelerate forever, tearing everything apart in a big rip.
But there is another theory. What happens if the expansion stops?
Stops entirely.
Yes. What if, billions of years from now, the collective gravity of all the matter in the universe finally overcomes the expansion, halts it, and begins to pull everything back together in a big crunch?
Wait, if the expansion stops?
If the expansion of space-time stops, those vital Hubble expansion velocities within extended objects vanish entirely. The cosmic velocity uncertainty drops to zero.
And according to Heisenberg's uncertainty principle, if the momentum uncertainty hits zero, the position uncertainty must approach infinity.
Exactly. Does the sudden halt of cosmic expansion cause the immediate catastrophic collapse of classical mechanics everywhere at once?
Oh my God.
If Herzenberg is right, the moment the universe stops expanding, the macroscopic world loses its anchor. Would human beings, planets, and stars suddenly lose their physical edges? Would we dissolve back into infinite, unlocalized probability waves, smeared across whatever is left of the cosmos in an instant?
Wow. That is something to ponder the next time you think you are just sitting perfectly still in your chair.
Absolutely.
There is no still. There is only the wave, the thermodynamic noise, and the vast expanding void keeping you pulled together.
It's a fragile, beautiful arrangement.
This has been an absolutely incredible deep dive. Thank you for taking this journey into the quantum classical boundary with us. Keep questioning the solid ground beneath your feet.